Casey, tell us about Gausslets.
Yep, Gausslets.
Molecular Hamiltonians and tensor networks. Yeah.
Cool. I'm Casey. I'm a PhD student in the math department at Dartmouth, but I work with physicists, specifically the Whitfield group, with my collaborator Weisher Wing, which is in the audience, and also James Whitfield. And I will mostly just be focusing, sorry to maybe disappoint people, focusing on the Gausslet and basis set part, but I'll also describe at the end current limitations for actually implementing this in iTensor. So to introduce this, we'll be looking at a new wavelet inspired basis set that was introduced by Stephen White, which you may know is the inventor of DMRG. And we'll look at the applications of Gausslets for electronic structure. And as review, if you haven't seen this already, if you're not as familiar with quantum chemistry, this is the first and second quantized Hamiltonians for electronic structure under the Born-Oppenheimer approximation. So the first part in the first quantization picture would be your kinetic energy of your electrons. The second would be the nuclear repulsion between your electrons and the nuclei of your atomic system, and the last would be the electron-electron repulsions. I'm sorry, I made a mistake. It's nuclear attraction between electrons and the nuclei. And we also have, if you're more familiar with maybe a second quantized picture too, we also have a second quantized picture of our Hamiltonian as well, and this time framed in terms of the creation and fermionic creation and annihilation operators, where this is written in chemist notation, since that's the one I like to stick with. What are some motivations behind using Gausslets, which are very kind of different basis set from typical basis sets you might have seen in quantum chemistry, familiar with that field. Typically, a big focus on that for molecular systems is this approach called linear combination of atomic orbitals, where the basic idea is, okay, a basis set that may describe an atom well, if we just sum over the different basis sets of the atoms, we could have a good description of our molecular basis set. This is a very different sort of basis set in that it allows for a systematic convergence to something we call the complete basis set limit in quantum chemistry. And one really nice property of this basis set that distinguishes from a lot of other ones is it actually diagonalizes the two-body interactions. So specifically, if you recall the previous slide, we see these elements right here kind of describe it's a rank 4 tensor of the different integrals you need to perform. For this particular basis set, this actually reduces the number of integrals you need to perform from order n to the fourth to order n to the squared. However, there is a large prefactor that comes because you need to add much more basis sets in order to kind of compensate. You can still also use Gaussian integral formulas since they're still come from a sum of Gaussians. And another nice property that ties into tensor network methods is it's a much more local basis set. So this has potential applications. Well, Stephen White has explored these a little bit, and I'm also trying to implement these in iTensor for tensor network methods like DMRG. And it also, to this point, has not been open sourced. I partly see why, because it's so difficult to reproduce. Being a mathematician, I also think that the mathematical properties of this basis set are really cool. So first, what is a Gausset? That's the formula on the top. You basically sum these CJs are your wavelet coefficients. You sum over those a grid of evenly spaced Gaussians that have basically are defined on a lattice. They have really nice mathematical properties as well that's described in subsequent work by Stephen White in the nested Gausset basis set property. Not going to go through all of these. One important one actually is this moment property. So they basically integrate like Dirac delta functions for low degree polynomials, and that's what gives you the two-body diagonalization that I talked about previously. But it turns out that just Gausslets alone on an evenly spaced grid are not enough to describe a molecular system. Specifically, if you're familiar with going back to kind of high school and studying the hydrogen atom, you maybe remember one part of the solution. The hydrogen atom is this e to the negative r, and we call that a Cuss condition around the nucleus. So it's actually really hard to have an evenly spaced grid that accurately describes Cuss. So instead, you need to distort your grid is one approach. This is kind of a little bit like doing a multi-scale kind of resolution analysis, but instead you stick with the same grid instead of making different grids, and you distort your grid in order to kind of adapt to the system that you have. So in particular, if we have just any continuously differentiable map, we can compose that map and include this Jacobian factor so we maintain orthonormality. And from this, we can make a new basis set that is distorted. And I'll show some nice pictures of this. In particular, one nice coordinate mapping to use is this inverse sine H map, which has this density, and this is a really nice map to work with because it approximately drops off like 1/x as you go away from a nucleus. So these are some pictures I made of Gausslets. So on the right is, you imagine this is a set of basis set. This is a Gauslet basis set on an evenly spaced grid. And then to the left, this is under the coordinate transformation. You see that the basis functions are now packed more. If we imagine having a nucleus at 0, and we need to describe like the nuclear cusp there, this packs the basis functions more tightly around that nucleus. And then this also is a visualization of a 2D grid. So we're also working with something called a Cartesian product basis set, which is ties really nicely to for implementing in tensor networks. This is the mapping for example, for if we have two nuclei, it's a much more complicated process actually constructing this. You can kind of roughly imagine summing them, but even though that's what they kind of state, actually in some of the papers, it doesn't work quite as well, so you have to do a little bit more complicated procedure. But you can see in this case now, actually, my basis functions are packed more tightly around both of my nuclei positions, but I still maintain all the nice mathematical properties I talked about earlier. Another thing to be aware of too, when you're working with this Cartesian product basis set, it's really important because I'm dealing with a ton of basis functions to decompose it as a product of 1D basis functions, and this makes the integrals a lot simpler to work with and manageable, because if everything was kind of mixed together, the integrals would quickly become unmanageable to deal with. So if you're just aware of a basic Gaussian integrals identities, this is actually a really nice way to decompose your Coulomb operator, and this is a really cool trick. And this is, for example, a test I did of just the hydrogen atom, which is nice to analyze, of course, because we know the solution in atomic units, it's just negative 0.5 Hartrees is the ground state energy. And one really cool aspect about this that we see is that actually nicely captures excited states too, even though I didn't actually state any specific information about the angular momentum. So that's really one really cool thing that pops out of this. Also, you can do like look at the landscape of the possible parameters, and that's one thing we want to work on in the future, is possibly doing automatic differentiation on the parameters of your basis set with using QuickBox, which is the main tool that we'll also talk about at the end, that was developed by Weisher Wing. So in this case, we see actually that decreasing that this bottom square is like the optimal choice for these two core and scaling parameters of your basis set. And this is really nice too, because I have a large number of basis functions, but I've correlated them just to 2 parameters. The iTensor implementation is still a work in progress. There's this package actually called iTensor Chemistry, which it seems which would be really nice to use. However, if you just look at the package, this is the first thing that pops up at the beginning. one thing that we kind of are able to tackle is that we are able, if you see right here, it has typically basis set scale like order n to the fourth for n orbitals. Well, like I said before, now we only have O n squared orbitals. However, now in order to actually tackle realistic systems, I still need to deal with thousands of basis functions. So this is still an ongoing work to actually implement this in DMRG, and particularly constructing the MPO using this basis set is currently unfeasible. However, there may be there still may be ways to still do this. Obviously, they were able to do this in the papers. So this is still ongoing work to try and have a native iTensor implementation of this. I think you can also take advantage of the locality of the basis set as well to maybe have a more manageable way to construct your MPO. And future work is constructing the MPO for electronic Hamiltonian using iTensor, doing parameter optimization using automatic differentiation, which Weisher will talk about on Friday, is you're able to do using his QuickBox package. And in general, I used QuickBox for a lot of these along with my own custom integrals. And this is something you really couldn't do in any other sort of basis set package because QuickBox allows you also to work with 1D basis functions and compose them really nicely as well. And one other thing that would be great to explore was that when is it advantageous to use something like a Gausslets basis set for quantum computing? If you're familiar with quantum computing literature and quantum chemistry, there's always an underlying assumption that they use like a minimal basis set like STO3G. So actually understanding how basis set discretization affects stuff like VQE would also be great to explore. Cool, thank you.
All right, questions for the speaker from the audience?
I don't know if you're aware, but iTensor chemistry is basically no more developed at the Flatiron. So I think if you're interested in taking it, you should like restart it. But right now, no one at the Flatiron Institute is directly working on this precise package.
Oh, okay, that's great. That's great to know.
So yeah, like if you really want to do something, you should consider starting your own package.
Yeah, that's what I realized pretty much. I think there's this other package though mentioned, this iTensor MPO construction that I think will actually be really useful for constructing the ops.
We should discuss more about the current state of iTensor then, I guess.
Yeah. Cool, thank you.
Cool. Other thoughts, questions?
Okay.
All right. Well, let's thank the speaker again.